Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence and robotics research. Today we're examining multimodal robotics, teaching machines to see, hear, and feel. We'll dive into 16 groundbreaking papers from July 3, 2025 that represent paradigm shifts in autonomous systems and human-robot interaction. These advances are moving us from simulation to reality, where robots learn through multiple senses, fundamentally expanding intelligent machine capabilities. Picture this. It's 2025, and a robot in a laboratory learns to pour coffee by watching videos and listening to the sounds of liquid hitting ceramic. It's never touched a real cup, never felt the weight of actual coffee, yet when presented with a brand new mug and a steaming pot, it pours with the precision of a seasoned barista. This isn't science fiction anymore. It's the reality of modern robotics research, where artificial intelligence is teaching machines to understand our world through multiple senses simultaneously, just like humans do. These 16 papers matter because robotics research sits at the intersection of artificial intelligence and pressing human needs. As we face an aging population and hazardous work environments, robotics offers solutions that enhance human capabilities while ensuring safety and efficiency. What makes this field truly fascinating is that every advance in robotics creates ripple effects across related fields, driving innovation in artificial intelligence. Sensor technology and human-computer interaction. Today's breakthroughs become tomorrow's everyday reality. Think of robotics research as a vast ecosystem, much like a bustling city where different neighborhoods represent different specialties. Computer science robotics sits at the intersection of the most vibrant districts, Artificial Intelligence Avenue, Mechanical Engineering Boulevard, and Human-Computer Interaction Street. This field, commonly abbreviated as CS.RO in academic circles, represents one of the most dynamic and interdisciplinary areas in modern technology, where researchers are essentially teaching machines to think, move, and interact with the world around them. The first dominant theme is multimodal perception and simulation, and it's revolutionary. Imagine teaching a child to cook by showing them only silent movies. They'd miss the sizzle that tells them when the pan is hot enough, or the bubbling that indicates water is boiling. Similarly, robots have traditionally learned from visual data alone, missing crucial auditory and tactile cues that humans naturally integrate. Researchers are now developing sophisticated systems that can combine sight, sound, and touch in realistic simulations, creating virtual training grounds where robots can learn multimodal skills before ever touching the real world. The second theme focuses on collaborative and cooperative robotic systems. Think of this like choreographing a complex dance where multiple partners must move in perfect harmony without stepping on each other's toes. As robots become more prevalent in our workplaces and homes, they need to work together effectively, both with other robots and with humans. This involves developing communication protocols, coordination strategies, and safety measures that ensure seamless collaboration while maintaining the trust and comfort of human partners. Motion planning and control optimization represents the third major theme, and it's like solving a three-dimensional chess puzzle in real time. Despite decades of research, creating robots that can move efficiently and safely through complex environments remains challenging. Current work focuses on developing algorithms that can handle the constraints of real-world physics, while optimizing trajectories on the fly and adapting to dynamic, unpredictable environments. This requires sophisticated mathematical frameworks that can process multiple variables simultaneously. These themes have yielded remarkable breakthroughs that are already changing the landscape of robotics. First, the successful integration of generative artificial intelligence models into robotic simulation environments enables effective zero-shot transfer from simulation to real-world environments. Second, hierarchical control systems now balance robustness and compliance in robotic locomotion. Third, advances in collaborative perception systems work effectively with limited communication bandwidth. Fourth, shared control systems guarantee safety while minimizing intervention in human operation. Fifth, three-dimensional Gaussian splatting techniques integrate with physical modeling for articulated object manipulation. Now let me tell you about a paper that truly exemplifies the revolutionary potential of current robotics research. Wang and colleagues have developed MultiGen, a groundbreaking framework that addresses one of the most persistent challenges in robotics, the simulation to reality gap for multimodal learning. This might sound technical, but the implications are profound. Imagine being able to train robots in virtual environments so realistic that they can perform perfectly in the real world without ever having practiced on actual objects. This represents a paradigm shift in how we approach multimodal simulation. The researchers' approach is both elegant and revolutionary. Rather than attempting to create perfect physics-based audio simulations, which would be computationally prohibitive, they leverage large-scale generative models to synthesize realistic audio conditioned on simulation video. Here's how it works. First, a physics simulator generates visual information about the robotic task. Second, a generative model trained on massive audiovisual datasets synthesizes realistic audio that corresponds to the visual simulation. This audio includes the sounds of liquid pouring, container interactions, and environmental acoustics that would naturally accompany the visual scene. The experimental results are remarkable in their demonstration of zero-shot transfer capabilities. The robots trained entirely in the MultiGen simulation environment successfully performed pouring tasks with novel containers and liquids in real-world settings. This represents a significant advance over previous approaches that required extensive real-world fine-tuning. But here's what makes this work truly exciting. The implications extend far beyond robot pouring. The MultiGen framework could be applied to robotic cooking, where audio provides feedback about sizzling and boiling, robotic assembly, where audio indicates proper part fitting, or robotic navigation, where audio provides information about environmental conditions and obstacles. As we look toward the future, the directions emerging from this research are both exciting and transformative. Think of the current state of robotics research as standing at the edge of a vast frontier, with multiple pathways leading toward different but interconnected destinations. The integration of generative AI with robotic simulation is opening doors to training environments of unprecedented realism. Collaborative robotics is evolving toward true partnerships between humans and machines. The advances in safety and robustness are paving the way for robots that can operate reliably in unpredictable environments, opening possibilities for applications in disaster response, space exploration, and other challenging domains where human presence might be dangerous or impossible. The research we've explored today represents more than just technical advances. It's a glimpse into a future where the boundary between artificial and natural intelligence becomes increasingly blurred. The 16 papers from July 3, 2025 collectively paint a picture of a field in rapid transformation, where traditional boundaries are dissolving and new possibilities are emerging daily. Whether it's through multimodal simulation, hierarchical control systems, or collaborative perception frameworks, researchers are solving fundamental challenges that have constrained robotics for decades. These breakthroughs are laying the foundation for a world where intelligent machines enhance rather than replace human capabilities. This analysis was synthesized using GPT Anthropic Claude Sonnet 4 2025-0514 with TTS synthesis and image generation via OpenAI. The The content has been reviewed by human experts for accuracy, though potential oversights may exist despite the review process. All original paper references are provided for verification. The research represents peer-reviewed work from the archive preprint server, ensuring academic rigor and transparency in the analysis presented. Subscribe to AI Frontiers for cutting-edge research analysis with weekly deep dives into breakthrough papers and expert analysis of emerging AI technologies. Join our community discussions on future implications, your gateway to tomorrow's innovations today. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.